Now that you know a little bit more about isotopes and how atoms have different numbers of neutrons in their nucleus to make these different isotopes, and how that ties in with a mass number and an atomic number, we're now going to look at how these different isotopes kind of average to get an average atomic mass or an average weight of what carbon weighs or nitrogen or oxygen. And those are actually going to be the masses that you see on the periodic table. So here we go. We start off with looking at the mass of an individual atom, and chemists developed a method of measuring the mass of an atom relative to the mass of a specifically chosen atomic standard. So they picked one atom and they called that the standard that they're going to measure the mass of everything else. And the standard is a carbon-12 atom. So all the scientists agreed that a carbon-12 atom has a mass of exactly 12 atomic mass units, or AMUs. Okay, so one AMU is 1/12 the mass of a carbon-12 atom. The mass of an AMU, or atomic mass unit, is very nearly equal to the mass of a single proton or the mass of a single neutron, but they are a little bit different. So as a result, the mass of silicon-30 is 29.974 AMU, not 30 AMU. So just because our mass number is a proton plus a neutron, and AMU masses are very close to the mass of those, they aren't the same. So we get these decimal answers for a mass for a certain isotope. When we look now at the periodic table, okay, and as you can see on this periodic table, each element has an average atomic mass, and as you can tell, they are decimal numbers. If you look at carbon, it's 12.01. If you see hydrogen, it's 1.01. And what those are is those are weighted averages of the isotopes of that element. So for example, if we have chlorine, the atomic mass of chlorine is 35.45 AMU. That's what it says in the periodic table. Well, chlorine exists naturally at 75% chlorine 35 and 25% chlorine 37. So we can there conclude that chlorine 35 atoms are in a greater abundance than chlorine 37 and affects the mass more because the mass itself is closer to 35. So the atomic mass, or average atomic mass, of any element is calculated by summing the products of each isotope's percent abundance times the atomic mass. So that's what we have listed on the screen here. Percent abundance times atomic mass plus the next percent abundance times atomic mass plus the next, depending on how many isotopes you have for a certain element. Some elements have lots of isotopes, like 10, 20. Others have 2 or 3. You do need to realize, though, that with the percent abundances, those are going to be not like 75%. You don't plug in 75. You'd actually put in 0.75. We change it kind of back from a percent to a decimal. Because that helium has 2 naturally occurring isotopes, helium-3 and helium-4. The atomic mass of helium is 4.003 AMU, and that is what is off your periodic table. Which isotope is more abundant in nature? Explain. So we talked about this before. This number is closer to 3, or is it closer to 4? Well, it's closer to 4, which means that there are more of the helium-4 atoms, or isotopes, I should say. If helium had a atomic mass of 3, then there would be more 3 helium atoms, or helium isotopes. Alright, so let's take a look at the next example here that says calculate the atomic mass of magnesium. The 3 magnesium isotopes have atomic masses and relative abundances of those 3 listed there. So, take our percent times our mass for all of them, add them all up, and that is your weighted average. So I've got 23.985 times 0.7899 plus 24.986 times 0.1 plus 25.982 times 0.1101. Take each one, add it up. should get 24.30 AMU. If you look on the periodic table, it's very close to that. Now, one thing to remember again is that these are decimal numbers. Average atomic masses on your periodic table are always decimal numbers because they are a weighted average. They're not this mass number plus that mass number, okay? They are these already decimal masses times their weighted average. All right, for our last example, we're going to actually work a little bit backwards because I have copper is made up of two isotopes. Coppers are Cu63, that's 62.9296, and notice how that number is not a whole number, but a number close to that whole mass number because protons and neutrons do not actually weigh 1. All right, so that 62.9296 is actually a decimal. And I have copper 65, which is actually 65.92 AMUs. Given copper's atomic mass of 63.546 AMU, which is the one that is on the periodic table, what is the percent abundance of each isotope? So the thing about this one is that you actually know my average. So I know my average should be 63.546 AMU. I know that. Usually that's what we're solving for. Well, since I know that, okay, normally I would take each isotope's weight times its percentage. So I have 62.9296. And I would take that times this percentage. Well, I don't know what that percentage is. That's what I call that X. And I would add to that the 65.9278. And that's going to be also times the percentage. Those percentages aren't usually the same. They're, I would say, almost never the same. So I call that one Y. So now it looks like in our equation that we kind of have two variables. So we've kind of got a problem here. We kind of should have another equation to help ourselves out here with our X and Y. Well, what do we know about X and Y? Okay, well, what we know about X and Y, okay, is that actually X plus Y, my percentages, should both add up to 1. Normally they'd add up to 100, okay, but actually they just add up to 1 because remember we changed those into decimals. Since I know that those are both adding up to 1, what I'm going to do is rearrange here so I have it in terms of one variable or the other. And I just picked X. So X is the same thing as 1 minus Y. Well, since I know that X is the same thing as 1 minus Y, I'm going to take this 1 minus Y, okay, and we're actually now going to plug that in as X. So then I would have Y's in both of them. So basically all we're doing here is a bunch of algebra. Okay, so sorry if you don't like algebra. All right, so I'm recapping. You got 63.546. That's going to be equal to 62.9296 times 1 minus Y plus 65.9278 times Y. So now I have both of them in terms of Y. So what you're going to do is we're going to have to distribute. So this is going to be times 1, and then that is going to be times my negative Y. So I'm going to change my color here, and we're going to go back, and we're going to look at 63.546 equal to 62.9296 minus 62.9296 times Y plus the other Y, 65.9278 times Y. So all you did was you just distributed out there. Now I got everything in terms of Y, which is great. Okay, I have this is something times Y, this is something times Y, so I can actually just combine them. And I can get rid of this, okay, by taking it to the other side. Well, how do I take it to the other side? You just subtract. So 63.546 minus 62.9296 is actually 0.6164. That's going to be equal to, and I combine my two Y terms there. That's going to be 1.9982 times Y. Okay, and that would be one. All right, 1.998. If I want to get Y by itself, all right, all I have to do is divide. I divide both sides by 1.9982. And I get my Y to be 0.308. Well, that's great, but what does that even mean? 308? Well, that's really my percentage. So that really means I have 30.8%. Well, when we look at Y, which one did Y go with? I went with the 65. So I've got 30% is going to be the copper 65. So that means the rest of my 100%, or if I take 1 minus the 0.308, because that's what that tells us up here, okay, 1 minus 0.308, I plug it in and I'll get the same percentage. So I would get 69.2% of the copper 63.